Medieval European interest in mathematics was driven by concerns quite different from those of modern mathematicians. One driving element was the belief that mathematics provided the key to understanding the created order of nature, frequently justified by Plato's Timaeus and the biblical passage, in the Book of Wisdom, that God had ordered all things in measure, and number, and weight. Boethius provided a place for mathematics in the curriculum in the 6th century when he coined the term quadrivium to describe the study of arithmetic, geometry, astronomy, and music. He wrote De Institutione Arithmetica, a free translation from the Greek of Nicomedes' Introduction to Arithmetic. De Institutione Musica, also derived from Greek sources, and a series of excerpts from Euclid's Elements. His works were theoretical, rather than practical, and were the basis of mathematical study until the recovery of Greek and Arabic mathematical works. In the 12th century, European scholars traveled to Spain and Sicily seeking scientific Arabic texts, including Al-Khwarizmi's The Compendious Book on Calculation by Completion and Balancing, translated into Latin by Robert of Chester, and the complete text of Euclid's Elements, translated in various versions by Adelard of Bath, Hermann of Carinthia, and Gerard of Cremona. These and other new sources sparked a renewal of mathematics. Leonardo of Pisa, now known as Fibonacci, serendipitously learned about the Hindu-Arabic numerals on a trip to what is now Baja, Algeria with his merchant father. Europe was still using Roman numerals. There, he observed a system of arithmetic, specifically algorism, which due to the positional notation of Hindu-Arabic numerals was much more efficient and greatly facilitated commerce. Leonardo wrote Liber Abaci in 1202, updated in 1254, introducing the technique to Europe and beginning a long period of popularizing it. The book also brought to Europe what is now known as the Fibonacci sequence, known to Indian mathematicians for hundreds of years before that, which Fibonacci used as an unremarkable example. The 14th century saw the development of new mathematical concepts to investigate a wide range of problems. One important contribution was development of mathematics of local motion. Thomas Bradwardine proposed that speed, v, increases in arithmetic proportion as the ratio of force, F, to resistance, R, increases in geometric proportion. Bradwardine expressed this by a series of specific examples, but although the logarithm had not yet been conceived, we can express his conclusion anachronistically by writing v equals log f/r. Bradwardine's analysis is an example of transferring a mathematical technique used by Al-Kindi and Arnold of Villanova to quantify the nature of compound medicines to a different physical problem. One of the 14th century Oxford calculators, William Heytesbury, lacking differential calculus and the concept of limits, proposed to measure instantaneous speed by the path that would be described by a body, if it were moved uniformly at the same degree of speed with which it is moved in that given instant. Heytesbury and others mathematically determined the distance covered by a body undergoing uniformly accelerated motion, today solved by integration, stating that a moving body uniformly acquiring or losing that increment of speed will traverse in some given time a distance completely equal to that which it would traverse if it were moving continuously through the same time with the mean degree of speed. Nicole Orisme at the University of Paris and the Italian Giovanni di Casali independently provided graphical demonstrations of this relationship, asserting that the area under the line depicting the constant acceleration represented the total distance traveled. In a later mathematical commentary on Euclid's Elements, Orisme made a more detailed general analysis in which he demonstrated that a body will acquire in each successive increment of time an increment of any quality that increases as the odd numbers. Since Euclid had demonstrated the sum of the odd numbers are the square numbers, The total quality acquired by the body increases as the square of the time. Renaissance, edit. Further information, mathematics and art. During the Renaissance, the development of mathematics and of accounting were intertwined. While there is no direct relationship between algebra and accounting, the teaching of the subjects and the books published often intended for the children of merchants who were sent to reckoning schools, in Flanders and Germany, or abacus schools, known as abaco in Italy, where they learned the skills useful for trade and commerce. There is probably no need for algebra in performing bookkeeping operations, but for complex bartering operations or the calculation of compound interest, a basic knowledge of arithmetic was mandatory and knowledge of algebra was very useful. Piero della Francesca, c. 1415–1492, wrote books on solid geometry and linear perspective, including De Perspectiva Pingendi, on perspective for painting, Trattato di Abaco, Abacus Treatise, and De Quint Corporibus Regularibus, on the 5 regular solids. Portrait of Luca Pacioli, a painting traditionally attributed to Jacopo de Barbari, 1495, Museo di Capo Diamante. Luca Pacioli's Summa de Arithmetica, Geometria, Proportioni et Proportionalità, Italian, Review of Arithmetic, Geometry, Ratio and Proportion, was first printed and published in Venice in 1494. It included a 27-page treatise on bookkeeping, Particularis de Computis et Scripturis, Italian, details of calculation and recording. It was written primarily for, and sold mainly to, merchants who used the book as a reference text, as a source of pleasure from the mathematical puzzles it contained, and to aid the education of their sons. In Summa Arithmetica, Pacioli introduced symbols for plus and minus for the first time in a printed book, symbols that became standard notation in Italian Renaissance mathematics. Summa Arithmetica was also the first known book printed in Italy to contain algebra. Pacioli obtained many of his ideas from Piero della Francesca, whom he plagiarized. In Italy, during the first half of the 16th century, Scipione del Ferro and Niccolò Fontana Tartaglia discovered solutions for cubic equations. Girolamo Cardano published them in his 1545 book Ars Magna, together with a solution for the quartic equations, discovered by his student Lodovico Ferrari. In 1572 Raphael Bomelli published his El Algebra, in which he showed how to deal with the imaginary quantities that could appear in Cardano's formula for solving cubic equations. Simon Stevens de Theory, The Art of Tenths, first published in Dutch in 1585, contained the first systematic treatment of decimal notation in Europe, which influenced all later work on the real number system. Driven by the demands of navigation and the growing need for accurate maps of large areas, trigonometry grew to be a major branch of mathematics. Bartholomeus Pitiscus was the first to use the word, publishing his Trigonometria in 1595. Regiomontanus's Table of Sines and Cosines was published in 1533. During the Renaissance, the desire of artists to represent the natural world realistically, together with the rediscovered philosophy of the Greeks, led artists to study mathematics. They were also the engineers and architects of that time, and so had need of mathematics in any case. The art of painting in perspective, and the developments in geometry that were involved, were studied intensely. Mathematics during the Scientific Revolution, edit. See also, Scientific Revolution. 17th century, edit. Gottfried Wilhelm Leibniz. The 17th century saw an unprecedented increase of mathematical and scientific ideas across Europe. Galileo observed the moons of Jupiter in orbit about that planet, using a telescope-based Hans Lippershey's. Tycho Brahe had gathered a large quantity of mathematical data describing the positions of the planets in the sky. By his position as Brahe's assistant, Johannes Kepler was first exposed to and seriously interacted with the topic of planetary motion. Kepler's calculations were made simpler by the contemporaneous invention of logarithms by John Napier and Jost Bürgi. Kepler succeeded in formulating mathematical laws of planetary motion. The analytic geometry developed by René Descartes, 1596–1650, allowed those orbits to be plotted on a graph, in Cartesian coordinates. Building on earlier work by many predecessors, Isaac Newton discovered the laws of physics that explain Kepler's laws, and brought together the concepts now known as calculus. Independently, Gottfried Wilhelm Leibniz developed calculus and much of the calculus notation still in use today. He also refined the binary number system, which is the foundation of nearly all digital, electronic, solid-state, discrete logic computers, including the von Neumann architecture, which is the standard design paradigm, or computer architecture, followed from the second half of the 20th century, and into the 21st. Leibniz has been called the founder of computer science. Science and mathematics had become an international endeavor, which would soon spread over the entire world. In addition to the application of mathematics to the studies of the heavens, applied mathematics began to expand into new areas, with the correspondence of Pierre de Fermat and Blaise Pascal. Pascal and Fermat set the groundwork for the investigations of probability theory and the corresponding rules of combinatorics in their discussions over a game of gambling. Pascal, with his wager, attempted to use the newly developing probability theory to argue for a life devoted to religion, on the grounds that even if the probability of success was small, the rewards were infinite. In some sense, this foreshadowed the development of utility theory in the 18th and 19th centuries. 18th century, edit. The most influential mathematician of the 18th century was arguably Leonhard Euler, 1707–1783. His contributions range from founding the study of graph theory with the 7 bridges of Königsberg problem to standardizing many modern mathematical terms and notations. For example, he named the square root of -1 with the symbol I, and he popularized the use of the Greek letter pi to stand for the ratio of a circle's circumference to its diameter. He made numerous contributions to the study of topology, graph theory, calculus, combinatorics, and complex analysis, as evidenced by the multitude of theorems and notations named for him. Other important European mathematicians of the 18th century included Joseph Louis Lagrange, who did pioneering work in number theory, algebra, differential calculus, and the calculus of variations, and Pierre-Simon Laplace, who, in the age of Napoleon, did important work on the foundations of celestial mechanics and on statistics. Modern, edit. This section needs additional citations for verification. Please help improve this article by adding citations to reliable sources in this section. Unsourced material may be challenged and removed. Find sources. History of Mathematics News Times Newspapers Times Books Times Scholar Times Chester, April, 2021. Learn how and when to remove this message. 19th century, edit. Throughout the 19th century mathematics became increasingly abstract. Carl Friedrich Gauss, 1777–1855, epitomizes this trend. He did revolutionary work on functions of complex variables, in geometry, and on the convergence of series, leaving aside his many contributions to science. He also gave the first satisfactory proofs of the fundamental theorem of algebra and of the quadratic reciprocity law. Behavior of lines with a common perpendicular in each of the three types of geometry. This century saw the development of the two forms of non-Euclidean geometry, where the parallel postulate of Euclidean geometry no longer holds. The Russian mathematician Nikolai Ivanovich Lobachevsky and his rival, the Hungarian mathematician János Bolyai, independently defined and studied hyperbolic geometry, where uniqueness of parallels no longer holds. In this geometry the sum of angles in a triangle add up to less than 180 degrees. Elliptic geometry was developed later in the 19th century by the German mathematician Bernhard Riemann. Here no parallel can be found and the angles in a triangle add up to more than 180 degrees. Riemann also developed Riemannian geometry, which unifies and vastly generalizes the three types of geometry, and he defined the concept of a manifold, which generalizes the ideas of curves and surfaces, and set the mathematical foundations for the theory of general relativity. The 19th century saw the beginning of a great deal of abstract algebra. Hermann Grassmann in Germany gave a first version of vector spaces. William Rowan Hamilton in Ireland developed non-commutative algebra. The British mathematician George Boole devised an algebra that soon evolved into what is now called Boolean algebra, in which the only numbers were 0 and 1. Boolean algebra is the starting point of mathematical logic and has important applications in electrical engineering and computer science. Augustin Louis Cauchy, Bernhard Riemann, and Karl Weierstrass reformulated the calculus in a more rigorous fashion. Also, for the first time, the limits of mathematics were explored. Niels Henrik Abel, a Norwegian, and Évariste Galois, a Frenchman, proved that there is no general algebraic method for solving polynomial equations of degree greater than 4, Abel-Ruffini theorem. Other 19th century mathematicians used this in their proofs that straight edge and compass alone are not sufficient to trisect an arbitrary angle, to construct the side of a cube twice the volume of a given cube, nor to construct a square equal in area to a given circle. Mathematicians had vainly attempted to solve all of these problems since the time of the ancient Greeks. On the other hand, the limitation of 3 dimensions in geometry was surpassed in the 19th century through considerations of parameter space and hypercomplex numbers. Abel and Galois's investigations into the solutions of various polynomial equations laid the groundwork for further developments of group theory, and the associated fields of abstract algebra. In the 20th century, physicists and other scientists have seen group theory as the ideal way to study symmetry. In the later 19th century, Georg Cantor established the first foundations of set theory, which enabled the rigorous treatment of the notion of infinity and has become the common language of nearly all mathematics. Cantor's set theory, and the rise of mathematical logic in the hands of Peano, L.E.J. Brouet, David Hilbert, Bertrand Russell, and A.N. Whitehead, initiated a long-running debate on the foundations of mathematics. The 19th century saw the founding of a number of national mathematical societies: the London Mathematical Society in 1865, the Société Mathématique de France in 1872, the Circolo Matematico di Palermo in 1884, the Edinburgh Mathematical Society in 1883, and the American Mathematical Society in 1888. The first international, special interest society, the Quaternion Society, was formed in 1899, in the context of a vector controversy. In 1897, Kurt Hensel introduced p-adic numbers. 20th century, edit. The 20th century saw mathematics become a major profession. By the end of the century, Thousands of new PhDs in mathematics were being awarded every year, and jobs were available in both teaching and industry. An effort to catalogue the areas and applications of mathematics was undertaken in Klein's Encyclopedia. In a 1900 speech to the International Congress of Mathematicians, David Hilbert set out a list of 23 unsolved problems in mathematics. These problems, spanning many areas of mathematics, formed a central focus for much of 20th century mathematics. Today, 10 have been solved, 7 are partially solved, and 2 are still open. The remaining 4 are too loosely formulated to be stated as solved or not. A map illustrating the four-color theorem. Notable historical conjectures were finally proven. In 1976, Wolfgang Haken and Kenneth Apple proved the four-color theorem, controversial at the time for the use of a computer to do so. Andrew Wiles, building on the work of others, proved Fermat's last theorem in 1995. Paul Cohen and Kurt Gödel proved that the continuum hypothesis is independent of, could neither be proved nor disproved from, the standard axioms of set theory. In 1998, Thomas Corlister Hales proved the Kepler conjecture, also using a computer. Mathematical collaborations of unprecedented size and scope took place. An example is the classification of finite simple groups, also called the enormous theorem, whose proof between 1955 and 2004 required 500-odd journal articles by about 100 authors, and filling tens of thousands of pages. A group of French mathematicians, including Jean Dieudonné and André Weil, publishing under the pseudonym Nicolas Bourbaki, attempted to exposit all of known mathematics as a coherent rigorous whole. The resulting several dozen volumes has had a controversial influence on mathematical education. Differential geometry came into its own when Albert Einstein used it in general relativity. Entirely new areas of mathematics such as mathematical logic, topology, and John von Neumann's game theory changed the kinds of questions that could be answered by mathematical methods. All kinds of structures were abstracted using axioms and given names like metric spaces, topological spaces, etc. As mathematicians do, the concept of an abstract structure was itself abstracted and led to category theory. Grothendieck and Serre recast algebraic geometry using sheaf theory. Large advances were made in the qualitative study of dynamical systems that Poincare had begun in the 1890s. Measure theory was developed in the late 19th and early 20th centuries. Applications of measures include the Lebesgue integral, Kolmogorov's axiomatization of probability theory, and ergodic theory. Knot theory greatly expanded. Quantum mechanics led to the development of functional analysis. Other new areas include Laurent Schwartz's distribution theory, fixed point theory, singularity theory, and René Thom's catastrophe theory, model theory, and Mandelbrot's fractals. Lie theory with its Lie groups and Lie algebras became one of the major areas of study. Non-standard analysis, introduced by Abraham Robinson, rehabilitated the infinitesimal approach to calculus, which had fallen into disrepute in favor of the theory of limits, by extending the field of real numbers to the hyperreal numbers, which include infinitesimal and infinite quantities. An even larger number system, the surreal numbers, were discovered by John Horton Conway in connection with combinatorial games. The development and continual improvement of computers, at first mechanical analog machines and then digital electronic machines, allowed industry to deal with larger and larger amounts of data to facilitate mass production and distribution and communication, and new areas of mathematics were developed to deal with this. Alan Turing's computability theory, complexity theory, Derek Henry Lehmer's use of ENIAC to further number theory, and the Lucas-Lehmer primality test, Rosa Peters recursive function theory, Claude Shannon's information theory, signal processing, data analysis, optimization and other areas of operations research. In the preceding centuries much mathematical focus was on calculus and continuous functions, but the rise of computing and communication networks led to an increasing importance of discrete concepts and the expansion of combinatorics including graph theory. The speed and data processing abilities of computers also enabled the handling of mathematical problems that were too time-consuming to deal with by pencil and paper calculations, leading to areas such as numerical analysis and symbolic computation. Some of the most important methods and algorithms of the 20th century are the simplex algorithm.
Yes. The camcorder's out of power. It's 8 p.m. soon. I think I should charging my camcorder a bit. Then I will cook some hot foods now and eating.